Our next speaker is our Name to Structure project leader at ChemAxon. He's got a computer science PhD. He's been with the company for 5 years, and I will do my best to pronounce his name correctly. Daniel Bonniot de Rousselet.
Okay, so this is an example of a document which has chemical names. Yeah, so here you see, so we're going to see all the things that we can do with names and documents. So here, well, let you read the text maybe. So here you have the name heroin, which is a traditional name, and here you have the systematic version of it. So what we can do the name to structure. So if you, oops, might work. So if you take this string heroin in itself, you can convert that to a structure. You can hopefully do the same with this longer IUPAC name. Then if you have a document, you have a prior problem, which is to find where in the documents occur the names. And so if you have the whole document, you will use a tool which will tell you that, oh, here it is. It's this. Using a dictionary, you can find that this looks like a name, or I know this is a name, and then I pass it to the name to structure. And the same problem when it's a IUPAC name. So this is the name extraction from document, or document to structure. This is the name of our product. And now we have the opposite problem, which is given the molecule, you can generate either the traditional name, or you can generate the systematic name for it. So we have products for all these three tasks. So structure to name is the product we released first, and it's quite mature. Here are some things that have been happening in the last year. There's support for isotopes. So generating from this structure, we generate the name with the isotope which is marked here for carbon, hydrogen, or any atom type. Here, this is a pseudo-asymmetric stereocenters. This is also something we can generate the name for now. We generate more traditional names when you choose that option. And there's been a speed up, so it's twice faster since 5.4, a bit last year after the UGM. And lots of smaller fixes. Basically, if you take a typical data set, you can convert at least 99.9% of your structures into some name. Sometimes the name could be improved because there are many ways to generate names, but it means that you can generate names for pretty much everything. I mean, especially in organic chemistry. In organic, it's still more limited. There's been much more action in the name to structure domain. So basically, when we try to improve it, we try to improve the coverage. So how many names we can understand correctly. That's my definition. So I count only those that are correct, if you have a standard of what the structure should be. And then there's the correction separately, that what's the percentage of those that you convert that are actually correct. You can convert that to precision and recall. That's just, I prefer to use these measures. So in 5.4 and 5.5, we had major upgrades to name to structure. So basically, bit by bit, most of it was rewritten. And it means that the coverage improved and the correction improved even more. We're going to see numbers. And again, in 5.6, coverage improved. So this is a typical, it's a database actually, it's from NCI, and you have a mix of systematic names, traditional names. And you can see that, so starting from, this is 1 year ago, this is 5.3.8, and we could convert a bit more than 70,000. And then with every major release, 5.4, 5.5, 5.6, we added more or less linearly more things that you can convert. These are all correct corrections. So the conversion is, the structure we generate is identical or up to tautomerism or things that are aromatic or not, identical to what's in the database. And this is the percentage of those that are not identical. So you can see that it dropped a lot in 5.4 and 5.5. Now it's still a little bit more than 5%. Part of the reason for those is there are still some errors in the software, but part of it is also that there are errors in the database. So I don't know what's the the perfect score that you could get, but I guess it's something like 2, 3, 4. I'm not sure. This is a different data set. This is names that are extracted from patents. And here you can see even bigger improvements because actually we focused less on that before, and now we focused more on it. So I could discover patterns of things that we didn't support, and now we do. So this 5.4, a bit more than 20,000 names could be converted, and it improved in 5.5, and then a big, actually from here to there, we actually didn't look at this data, and here we had a look. Obviously, we don't do one by one, but still, it was very useful to get some data and that we could find the things that we don't support. And the agreement here, it's quite interesting because those structures, as far as were generated by a competitor tool. And so this is the rate of agreement that we had. And so in 5.4, we had only 50% agreement. And this went up to 60, and then now we are almost 70%. So clearly, the increase that you see here is because the quality of the structures we generate is improving. But still, it's pretty low. So it means we have more than 30% of the cases where we don't generate the same structure as this competitor. And so the question arises, who is right? This is, basically I took a random sample of those cases that are when we disagree, and asked chemists, what do you think? And so the answer was first that about a quarter of those cases were actually ambiguous. And I think a big reason for that is that those names that come from a patent, because there's this first step of finding the boundaries of the name. If the tool gets it wrong, or if there is some noise in the text of the patent, then there's actually only a portion of the name, which means that maybe the locant missing. And so the name is actually ambiguous, and you cannot say who is right or wrong. But 3/4 were not ambiguous. And so this part, this is now what we focus on here. You can see that both tools were wrong in 6% of the cases. And then the competitor was right in a quarter of the cases, 25%, and then we were right in 67%. So it's quite an encouraging result. It's a partial result, so don't assume that it will be the same for every set and with every tool. Obviously, it's something we want to do more comparisons, and obviously it's always a driver for improvement. Finally, you can see that there is 2% where the chemist said that both are correct, even though they are not the same structures, and my program thought that they are not correct. So, but it's pretty rare. Now, in documented structure, we also provide this tool. And so it extracts the names from text documents and returns the structures and their location. If it's a text document, it can tell you exactly which character. If it's a PDF, it will tell you just the page number because there is no really definition of location more than that. We do some OCR correction. This is a pretty interesting case where you see that here, for instance, the M was recognized as RN, and then the 1 is a L, and then there is a space here and a dash, so it's a pretty dirty name, but this is something we can recognize. It doesn't always work, obviously. We also import the smiles and INCHI in the documents. And since 5.4, we extract names from PDF documents, and since 5.6, you can actually open the PDF in Marvin View, and so you have a view of all the names that were found in the document. Tomorrow I will do some demonstrations and a presentation about this in the user training. The things that are coming, well, in name to structure, they will be, as before, more coverage and correctness. There is a feature request to, basically when you have these ambiguous names, you can decide to be strict and reject them, or you can decide to convert as much as possible. Maybe decide arbitrarily to connect a substituent somewhere. And actually, different people want different results. So we will actually provide the options to put the scale somewhere between very strict and very permissive. And you can actually filter afterwards how you want to deal. You could actually deal with it differently. In documented structure, there will be speed ups. There are things that are in work in progress on this. and more also error correction. In structure to name, also there are a few requests for improvements, and maybe I will add 1.9 in the rate of conversion. And yeah, this is a picture of me in the plane coming here, and I was designing D2S version 2.0. So this is a work in progress. And yes, I just want to thank different people who have been evaluating and using our software. I've been sending data, and it's very, very useful for us to test and to improve. So all these people have been helping, and so these companies. And at ChemAxon, we have now a chemist who is helping, and she has been doing a lot of the work in improving.
Any questions for Daniel?